Hello and welcome everybody to this plenary talk of the ICM. I'm Sylvia Surfati from the Quant Institute at NYU. And it is my real pleasure to introduce my former classmate and friend, Laure Saint-Raymond, who is currently a permanent professor at IHES. She has received many prizes and awards. I won't list them all. And she's a member of several academies of sciences. For instance, she was the youngest ever elected to the French Academy of Sciences at the age of 38, I think. Laure is famous for her work on kinetic equations, in particular for solving Hilbert's sixth problem by deriving the Euler of Navier-Stokes equations of fluids as limits of the Boltzmann equation of gas dynamics, and also for her program with Bodino, Gallagher, and Simonella on fluctuations and correlations for gas equations, which is what she's going to be talking about today. She's also famous for her strong ethics and her bold stances, in particular in favor of more collaboration to move science forward on this topic. I invite you to watch the video of her now famous speech in front of the French Academy of Sciences. Her title today is Dynamics of Dilute Gases, a Statistical Approach. We will be taking maybe some questions at the end if time allows. And Laure, the microphone is yours.
Thank you very much for this very kind introduction. So what I would like to do first is to thank the program committee for this great invitation, and also all the local organizers last week in Helsinki and now in London for the opportunity of giving this talk in front of a live audience, which of course is much better than just being in front of your laptop. So I think actually, even though it's not like a usual ICM, it's very nice to have this smaller events and somehow to celebrate mathematics. So, well, of course, in this very dramatic circumstances, I also feel that we cannot do our business as usual. So I would like also to just express my sympathy for, so nothing is working. Okay, thanks. So yeah, I would like to express my deepest sympathy and also somehow my solidarity with all victims of Putin's regime. Of course, there is not much that I can do, so I will now jump to my little story about gas dynamics, but I feel it was important as well to mention this now. Okay, so I guess everybody more or less knows what a gas here, or at least that there are a lot of gases surrounding us. And so it's a very natural question to know how we can describe a gas and also maybe also just predict its evolution. So actually there were many attempts to do this kind of things, and I will not say look at them in a historical order, but just at looking at different scales. So of course you can consider a gas to be a big collection of very small particles, so maybe atoms or molecules or maybe even smaller, and then just say that you will describe motion of all these small entities using either classical mechanics, so Newton's principle, or even quantum mechanics, but here I will not focus on this quantum effects. So, but of course we will see that this is not a very effective way of describing a gas. And so actually very long time ago, there were other models that have been introduced. So there are fluid models. So they have been introduced, for instance, by Euler or Navier and Stokes. Just considering that, of course, you have this big collection of particles, but you can also consider the gas as a continuous field. Okay, and then just consider some kind of big particle of, say, fluid, and you are not interested in the motion of the small particles in this volume, but just at, say, the bulk velocity of this kind of big particle of water of a gas, okay? And somehow there is an intermediate description, which will be somehow the focus here in this talk, which is, so you see the first description is you look at this very small element of fluid, then you see all the small particles inside this volume, and you just try to describe all velocities of all particles. Then in this model here, you are just interested in the bulk velocity of all these particles in the small volume of fluid. And here, it's kind of intermediate description where you are interested in the distribution of velocity. So you are not interested in each velocity of each particle, but just the distribution of velocities inside this small volume. So this is just counting the number of particles with such or such velocity. Okay, so these are three different levels of description, and there is a very natural question which actually was raised by Hilbert in his sixth problem, which is to know whether all these descriptions are consistent with each other. Okay, so do they predict the same kind of behavior? Of course, you expect that the answer is yes, but this is still a very open problem. And so now what I would like to discuss is this first arrow here. So to understand the connection between the microscopic description, so just looking at all particles, and now this mesoscopic description, where you are just interested in this statistical approach of the same thing. Okay, so I will start by describing a bit more my starting point, which is molecular dynamics, so microscopic dynamics. But of course, I will try just to focus on the simplest possible model. Okay, and this simplest possible model is just a gas of earth spheres. So this means that at the microscopic level, you assume that, say, all atoms are just like spheres like this, and their motion is essentially just to go in a rectilinear uniform motion. Okay, so they just move with their own velocity, which is constant, until they collide with another particle. Okay, so that's really a simple model. And then you have, of course, to prescribe what happens when they collide. And here you will just consider that your molecules are just like billiard balls. And so they will be deflected. Of course, just think about a billiard. And what you require is that both the total momentum, okay, so the sum of the velocity, and the kinetic energy, so the sum of the square velocity, are conserved in this collision. Okay, so if you assume that you have both this condition plus the fact that the particle cannot overlap, then you end up with a very simple law here, which is this law of elastic collision. Okay, so this is really say the simplest possible model somehow, and it enjoys very nice features such as the fact that, of course, the total energy is conserved, and this is really like an Hamiltonian system, even though it's a bit singular, because you see that these collisions they happen for at a pointwise time and pointwise also in space. Okay, so anyway, you see that you have a very simple way to write the ordinary differential equations which govern this system, which is just the fact that the derivative of the position is the velocity, which is just a definition of the velocity actually, and the fact that the derivative of the velocity is 0 until you have a collision. Okay, so apparently this system is very simple, and so you can decide that you are very happy with this. But we will see that it's not as easy as it could look, because, of course, then we will be interested in the case where these particles are very small and you have a lot of them. Okay, so the first thing that I would like to show you is this video, and I am very grateful to Francis Philbay, which actually does the whole thing. Okay, so this is just to show you this an example of this dynamic. So here you see that this particle, they have colors, but this is just to help you just viewing the trajectories of the different particles. So you see, you start from these particles, and at the very beginning, the colors were ordered, okay? And now you think that they somehow mix up. Okay, but now if you just try to reverse all velocities, so now you see that you have all these particles, you just stop at this time, then reverse all velocities and do the same thing, so same dynamics, then you get this one. Okay, so I just go back in time, okay, and then you see that the particles evolve according to the same law. Actually, just the velocities were revert, and so normally, if you wait the end of this video, you end up with exactly the same. Okay, this doesn't work. I don't know why. Okay, but you should end up after exactly the same time by, and you will end up with exactly the same situation as the very beginning of the first one. Okay, so this means that if you evolve during a time t, then just reverse all velocity and evolve during a time t, and you are exactly back to the initial situation. And that's what is called reversibility for this dynamics. Okay, so that's important, a very important feature actually of this system. And it's also related to this Poincaré recurrence theorem. Okay, so the problem is that actually here I'm cheating because I didn't really, so first of all, I did nothing, but actually this numerical simulation is not really a numerical simulation in the sense that you just saw the video in a reverse sense. Of course, you are back to the initial data, but if you try to, for real, do the same numerical situation, just because of very, very small errors in this numerical simulation, you will never go back. Okay, so you see that it tells you that there is something which is very difficult with this system. It is that it's very sensitive to any small error. Okay, so it's somehow very unstable. And so that's the next point that I would like to explain. Okay, so I will try to explain this small picture here. So imagine that you have this particle here and say that it's fixed, like an obstacle, okay? And now you have this green particle here, and okay, it will arrive with a velocity, which is like this, and then it will hit this black particle, and it will be reflected according to this trajectory here. Okay, so that's just like billiard balls. You look at this elastic collision law, and you get this. Okay, now if you just start with the blue particle, which is almost like the green particle, except that you just move it a little bit, okay, then you see that you will also collide with the black particle, but then you will be reflected in this direction here. And so you see that after the reflection, after the collision, the two trajectories will be completely different. Okay, and of course you see that if this, so this distance is typically of the size of the particle here. And so if you consider a system where the particles are very, very small, then you see that a very, very small error will completely change the trajectories. Okay, and you have no, say, there is no way you can avoid this problem. Okay, and so you see that in this video, this is exactly the case. You start with essentially configuration which are really, really close to each other, but then you wait a little bit, and then you see that they have nothing to, there is no mean to couple these two trajectories. Okay, they are really far from each other. Okay, so that's really, say, a very important feature of this system, and you see that it's also somehow a big problem if you are interested in predicting the dynamics of your system, because first of all, you have a lot of particles, so you have a big system of equation. So that's the first problem for the numerical computation. And the second problem is that because of this instability, actually you don't really know what you will be able to predict. Okay, probably nothing. Okay, so that's the problem with this microscopic description. And so now what I would like to explain is what is this statistical description that I mentioned, so which is essentially related to this Boltzmann kinetic theory. And then I will try to explain why it is supposed to be a good approximation of this microscopic dynamics. Okay, so there is a first remark that, okay, in this gas, you have a lot of particles, but actually you are not really interested in the position of each of them. Okay, and in particular, you are not interested to know whether this particle has label number 1 and this one is labeled with label number 2, or this, if you exchange the two particles, essentially you see that this is the same configuration of the gas. Okay, so this kind of exchangeability between particles is very important, and it will be, of course, very important if you are interested in the statistical description, because you can make statistics about population where, say, somehow all the guys are more or less the same. Doing statistics where if all the particles are different, it's maybe not very interesting. Okay, so so the quantity we will be interested in is what is called this Amplicon measure. So somehow it's an average, okay, a distribution of particle. So that's what is defined here. So it's a measure that you can expect. So it's a measure which somehow is defined on the phase space. So the phase space here is the space with, say, d coordinates of position and d coordinates of velocity. Okay, so it's a 2D dimensional phase space. Okay, here, so you have a measure on this phase space, and it's defined as the average. So you see that you have 1 over n, which is the number of particles, times the sum over I from 1 to n of the direct masses at. So here you see that's the position of particle I, and here the velocity at particle I. Okay, so just imagine that you have your phase space, and you put just a direct mass each time you have a particle. Okay, and then you average, and this gives you the Amplicon measure. So this quantity, you see, it's really like an average. And so if you think about statistical description, it should be a very nice object, okay, because it's an average. So you expect by this law of large numbers and things like this, that it should behave in a nice way. Okay, and the other thing is that, okay. So now the other thing is related to this property or this feature. Maybe it's a bad or it's a nice feature. That's something that we should discuss afterwards. But so we see that it's not completely clear how you can describe very precisely the trajectory of your system, and then you will have the same problem somehow with the Amplicon measure, just to say what is the initial value of this Amplicon measure. Okay, because if you shift just a little bit the position of one particle, then we expect that the trajectory will be completely different. Okay, and so for the same reason, actually, you are not completely able to observe just the Amplicon measure at a given time. And so essentially the information that you can know about this system at time 0 is more like an information about the statistical distribution of all these particles. Okay, so this kind of thing that you can measure is what is the typical distribution of particles in this phase space with x and v variable. Okay, and so I will call this distribution distribution of typical particle f naught. And since I don't know anything about this, say the joint probability of all these particles at time 0, I will just assume that they are independent at time 0. Okay, so now you see that I have this system, which is a deterministic system where all the particles will evolve according to this very simple ODEs that I mentioned at the very beginning. But now I have a bit of uncertainty on the system, and this uncertainty is due to the fact that at time 0, I don't know exactly the position and the velocity of the particles. And so I will, instead of prescribing one configuration at time 0, I will look at, say, a whole family of possible configuration, and I just put a probability density on this family of configuration at time 0. Okay, so now I have a deterministic system, and I have a bit of randomness on the system, not due to dynamics itself, but really to the fact that at time 0, I should, okay, oh, sorry, it was, yeah, here. So at time 0, what I assume is that particles are distributed according to this f naught. Okay, so this is the probability of a typical particle. I say that since I don't know anything about these particles and how they are correlated, I just assume that they are not. Okay, so now the probability of having both a particle at position x1, v1, and another particle at at position x2 with velocity v2 is just a product. Okay, so they are independent random variable. Okay, so that's what is written here with this product here. Okay, of course I have to just modify this a little bit because the only thing that I know is that the particles cannot overlap. Okay, so I modify this tensor product here by the fact that here the particles cannot overlap. And then I say that actually there is still another thing that I don't really know at time 0, which is the exact number of particles. Okay, so what I know is that I have an idea of the typical number of particles, the average number of particles, but the precise number of particles I don't know. Okay, I cannot count the number of atoms in this room. Okay, so I don't know. I can say, okay, the typical density of the air in this room is this or this, and then I can estimate the average number of particles, but certainly I cannot measure. Okay, so that's why here we assume that the number of particles is also a random variable, which is given by this Poisson log. Okay, and then of course I need to this to be probability density, so I need to normalize. So this z epsilon is just the normalization of this density. Okay, so you see that there are two important features. That first of all, it's chaotic, meaning that you have this factorization here, or this quasi-factorization. And the fact that it's quasi-Poisson, so you know that the number of particles is given by this Poisson. Okay, so now we are somehow all set with this statistical setting. So we have this deterministic dynamics, a statistical distribution at time 0, and now we can ask different questions. So the first one, so here I will assume further that we are in a special regime where I expect typically that particles will have, so each particle should have essentially one collision per unit of time. Okay, so this choice, so it relates the size of the particles and the typical number of particles, and it tells you that essentially what you expect is one collision per particle and per unit of time. Okay, so under this scaling assumption, I will be interested in 3 questions, which are very natural questions in probability. Okay, so now I know that at time 0, I have this distribution of configuration, and now I would like to know how it will evolve. So what is the typical distribution of a particle at further time? Okay, so what is the law of typical particles when this number mu epsilon goes to infinity? So you have a larger and larger system with smaller and smaller size, and you would like to describe this law. So of course, this is what is said. It's just a law of large numbers for this dynamical problem. But of course, if you imagine that you are interested in the dynamics of this gas, for instance, to compute the re-entrance of a spatial vehicle in the atmosphere, you are not really interested in what will happen in average. Okay, what you would like to know is what will happen for real. Okay, so then there is another question: is this average a good approximation of what will happen for real, or it's just the average? Okay, so now the question is how the system can fluctuate around this average. Okay, so that's the typical question you ask when you are looking at central limit theorem. So what is the size of the fluctuation? And can you say something about the dynamics of this fluctuation? And so this will be question 2, which is, can you say something about a central limit theorem for this dynamical system? Okay, and then question 3 is maybe even more important if you think about this problem of re-entrance of a spatial vehicle, because what you would like to be sure is that it will not just go completely in the wrong direction. And so the question is, what is the probability to see an event which is very far from the average? Okay, and so this is related to what is called usually a large deviation principle. And so this is also a question here: can you see something which is completely different from the average dynamics? Okay, so that's really how you can somehow describe with mathematical statements this arrow that I mentioned in the first slide. So you start from the microscopic dynamics and you would like to end up with a statistical model. Okay, so next, what I should tell you is what can you say for this statistical model, what this statistical model is. So now if you would like to write an equation, it will be much more complicated. And of course, here I think this talk is supposed to be for a very broad audience. So what I would like to give you is more like an intuition of how the things should go, more than very precise mathematical statement. Okay, so oh, there is this. So this space was not supposed to be here. So the Boltzmann equation actually is supposed to describe the statistical behavior, the dynamics of the particle. So you don't know very well the initial configuration, but then you would like to say what should be the motion of a typical particle. Okay, and so what you expect is that actually it will behave, of course, in a similar way as at the microscopic level. So you start with your particle here. You so it will just be transported with this rectilinear and uniform motion until it will collide with another particle. But of course, here you describe just one particle because it's just like a projection on just one typical particle. So you say that, okay, maybe at some point and after a random time, and this of course you need to say something about this random time, it will be deflected by a collision. Of course, you cannot describe very precisely this collision because you don't know exactly where the other particles are, but say what you expect is that after some time it will be deflected like this, and then have this straight motion, and then another deflection, and so on. Okay, so essentially what the Boltzmann equation tells you is that you will have this kind of stochastic motion. So now the dynamics itself is somehow stochastic. Okay, it's very different from the microscopic dynamics, which is deterministic. And so what you have is a kind of combination of transport. So this part is very easy to describe. And this kind of random jumps. Okay, so sometimes after a random time, the particle decides just to jump to another velocity. Okay, and so of course you expect these jumps to be due to a collision with other particles. And if all these particles are independent of each other, then you expect the transition rate to go from one velocity v to one velocity v prime to be proportional to the local density of particles. Okay, and actually for art spheres, you expect this transition rate to be given by this complicated thing. So the only thing that you should look at here is that this transition rate, of course, depends on the number of particles which locally have the velocity v1. Okay, and then it will tell you how many, say, what is the chance for this particle to have a jump. Okay, so that's more or less what is encoded in this Boltzmann equation. Okay, and so now I would like to just show you what happens if you just try to simulate or compute this Boltzmann equation. So here, this is a very, somehow it's kind of a very school case somehow, where you start with all particles essentially at the same point. Okay, so that's the repartition in the X space, so the localization, the spatial localization of your particles. And this is just their velocities. So this is the distribution of velocities. So here you see at time 0, you start with essentially two velocities, one which is negative and the other one which is positive. Okay, and then just let's look what happens. So of course you see that there are two important things. The first one is that you have this dispersion of particles, so they will go in all directions. And after a while, essentially what you expect is that you have kind of uniform distribution of particles. Okay, so you start from something where everything is concentrated, and after a while, essentially everything is uniformly distributed. And you can also look at the distribution of velocities. So we started with essentially two velocities, and after a while, you have something which is a nice curve. And actually, if you wait for sufficiently a long time, then you expect this distribution to be like a Gaussian. Okay, and that's actually what is predicted by the Boltzmann equation. If you start from any nice distribution, then you should relax, okay, towards an equilibrium. And this equilibrium is essentially, in this case of a torus, just something which is uniform in X and like a Gaussian in V. Okay, And so you see that there is something which is very surprising, that it's supposed to be a very good approximation of our microscopic dynamics, but you have very different features. If you remember, I show you this first video where you saw that for the microscopic dynamics, you can go forward and then backward, and then you go back to the initial dynamics. And so in particular, you don't expect to have convergence towards an equilibrium. Of course, if you converge towards an equilibrium, then after a while, essentially all the distributions are the same, and there is no reason that you can just go back to something which can be different at time 0. Okay, so this somehow is very surprising, and actually it has been the source of big controversies in the mathematical and physical communities for more than 1 century. So after the work of Boltzmann. And so this is really somehow kind of not like a technical problem, but just really a conceptual problem to understand why you have this apparent paradox between these two descriptions of the same gas. Okay, but nonetheless, it was proved, and actually, I think it's so. This result is not perfect for sure, but it's somehow a very important conceptual advance. It was proved by Lanford something like 40 or 45 years ago, that if you look at this low density limit, so meaning that you have this Boltzmann grad scaling and mu epsilon goes to infinity, then you can look at your Amplicon measure, which was the object that I defined at the very beginning. Okay, so I just recall that it's just 1 over mu epsilon, which is a typical number of particles, times the sum of the Dirac masses. So when you test on a function h, this is just this observable here. So you can prove that this guy will concentrate on the solution of the Boltzmann equation. Okay, so this means, so what I mean by concentrate on the solution of the Boltzmann equation, that if you look at the difference between this Amplicon measure tested on this function h and the average of h against the solution of the Boltzmann equation, so the probability that this distance here is bigger than delta, converge to 0 as mu epsilon goes to 0 to infinity. Okay, so this means that you can start essentially with any configuration that you would like. Okay, if you look at this average, say if you are lucky, and so but you are lucky with probability almost 1, you will be very well approximated by the solution of the Boltzmann equation. So unfortunately, the problem with this result is that it's true, at least it has been proved to be true only for very short times, which is a very important restriction from the physical point of view. But still, you see that somehow it tells you that there is no paradox. Okay, so that's one of the things that I would like to explain now, is why there is no paradox. What is encoded in this approximation, and what can you do, okay, to know a bit more than just the average? Okay, so is it possible to answer also question 2 and 3? Okay, so all this is related to the problem of correlations in this gas. So first of all, I would like to just read again this statement by Lanford and try to explain what it tells you about this correlation and why it's not a problem that you have this description which is somehow irreversible, while the underlying dynamics should be reversible. Okay, so this is a bit more technical, but I will try to explain as far as possible. So the first thing that is important, okay, is that when you are able to prove this convergence of the Amplicon measure, then essentially what it tells you as a corollary, okay, is that now if you look at 2 points, so 2 particles, okay, and you look at their distribution, their joint distribution, okay, after say a time t, then what you can prove, and actually it's just equivalent to this statement that I just mentioned just before. Okay, so the joint probability of having one particle at some point in the phase space and another one will be just the tensor products. Okay, so when you have the convergence of the Amplicon measure, then what you can prove is that if you look at any finite order correlations, then what you expect that essentially you don't have any correlation. So the particles just keep their initial independence. Okay, so I just recall you that I started from a distribution where I know at time 0 that all the particles are independent. This is just my assumption. Okay, and now what this theorem tells you is that after a time t, okay, you cannot say, of course, that all the particles remain independent. This is just wrong. But if you just look at a finite number of them, then they will be independent. Okay, so you keep this factorization provided that you just look at a finite number of them. Okay, so that's just a corollary of Lanford's theorem. Okay, so that's what is written here. And so in this community of, say, statistical physics and kinetic theory and so on, people say that chaos is propagated. So I think I know that I should be very careful with this terminology of chaos, because depending on the different mathematical communities, this word can correspond to very different things. Okay, but here, when you say that chaos is propagated, it means that somehow you keep the independence between the different particles, provided that you just look at a finite number of them. Okay, so, and you see that this property actually can be seen in the Boltzmann equation. Of course, I didn't write it, so it's a bit complicated, but if you remember, maybe I can try to go back. Yes, here. So you see that what I said is that the probability that this particle here has somehow a jump here is proportional to this, so the transition rate is given by this f. Okay, so this means that actually, of course, you will have a jump if you have at some point, at some time, you have two particles which are essentially at the same point. And okay, they have velocity, say v and v1, and they will jump to something else. Okay, so what you need to know is the jump probability of having two particles at the same point. Okay, and what the Boltzmann equation somehow assumes is that this probability, this jump probability, is just a product. Okay, so that this transition rate is just like a function, so it depends on just this probability density. Okay, so it's really important to understand that the Boltzmann equation, and actually this was really, at the time of Boltzmann, this was not like a derivation of an equation from something else. This was just, Boltzmann assumes that you can describe your gas with this equation, and actually it was really stated like an assumption that you have this chaos. Okay, so that you can say that the probability of having a jump is just like, should be the jump probability of having two particles, and it's just like the product. Okay, so this is really something which is important here. And so this is encoded in this Lanford theorem that essentially the collisions will involve uncorrelated particles. Okay, but of course, it's not true that particles will remain uncorrelated for all times. Of course, if you have a collision like this of these two particles, just after the collision, now they are correlated because they just saw each other in the past. Okay, so somehow it's not true, and it cannot be true that all particles will remain uncorrelated. So of course, you know that there will be correlations. And so this picture is supposed to describe this correlation. So here I look at a large number of particles at the time t, and now I look at their past history. So I just go back, and you see that these two particles, actually, they are correlated because at some point they just had a collision. Okay, so these two particles, they are correlated. Okay, and the point is that, of course, if I choose at random two particles, probably they will not be correlated because there are a lot of particles, and each particle, I've seen just a finite number of them during my time interval. Okay, so this is really related to this dilute assumption, so that you don't have, so you have a lot of particles, each of them have a finite number of collisions, but in the end, if you take two particles at random, there is no reason why they should be correlated. Okay, but this correlation, they exist. Okay, so here this is a very specific case where I just try to figure out that there were a lot of collision in the past, and so all the particles, more or less. So you see that all these particles can be correlated. Okay, but you see that. So another way to rephrase this thing is that in order that two particles are correlated, you need to have very strong geometric constraint. Essentially, two particles will be correlated if in the past they had a collision, or maybe these two have a collision, but of course, this particle is also correlated with this one, because this one has a collision with this one, and then this one has a collision with this one. Okay, so you see that it's not just like having a collision together, but also you can have your parents which have collided together and so on. So this is just being in the same cluster of collisions. Okay, so this notion of clusters is very important to describe these dynamical correlations. And you see that actually being in the same cluster, it imposes very strong geometric constraint on the particles. Okay, so now I try to just explain why what is really studied in this Lanford theorem. So what it tells you is that you see that this measure will converge, but what you expect is that actually it will converge almost everywhere. Okay, and so there are very tiny subsets of the phase space where maybe it's not true. Okay, where for sure actually it's not true, and so this means that essentially, if you take things at random, so two random points in the phase space, then you have no correlation. But now, if you choose this subset very carefully, then you will see the correlations. Okay, so the correlations, what it means is that they are supported on very singular sets. Okay, so of course, if you test on a continuous function, you will never see these singularities, and you end up with a Lanford theorem. But now, if you would like to say more about the system, or so if you would like to retain a bit of information about this correlation, then you have to look at these very singular subsets. Okay. So this was the first. Maybe I just should go back here, because the only thing that you need to remember from this slide here is that this correlation, they are negligible in average. Okay. As soon as you look at an average against a nice test function, you will not see the correlations. So that's the first lesson. Okay, so there is essentially no contradiction between Lanford's theorem, which tells you that in average, you will not see the correlation, and the fact that the system, of course, have some correlation. Okay, so now the second thing, and it will explain the problem of irreversibility, is that even though this correlation, they are supported on these very, very small sets. Okay, so we know that this correlation, they are encoded in small sets, and that's why they are negligible in average. Still, they encode a macroscopic part of the information. Okay, so that's really important. And you see that it's related, of course, to different notion of functional spaces and things like this. But what is important is that even though they are supported on very singular sets, they encode a macroscopic part of this information. Okay, so of course, you see that if you would like to go back, okay, so if you go back to this picture, which is here, you see that if I would like to reconstruct the backward dynamics, of course, I need to know something about this collision. And so I need to know something about the correlations. Okay, so somehow the information that you need to be able to reconstruct the backward dynamics, so not to lose the reversibility, is exactly this information that somehow you just throw away in a Lanford theorem. Okay, so that's really important that this correlation, they encode the backward dynamics and actually a macroscopic part of the information. So this part of the information which is somehow lost is corresponds exactly to this entropy. Okay, so Boltzmann's equation actually has an H theorem, that's the name, which just tells you that there is a Lyapunov functional for the evolution, or that you have a second principle of thermodynamics. So it depends on what is your background, but everything here is the same. But what is important is actually the fact that you have this entropy, so dissipation, we say in mathematics, is actually an entropy. So in physics, the entropy is increased. So everything, so all this kind of things are different in mathematics and physics, but of course, it's the same in the end. Of course, so you see that this entropy, the fact that the entropy is increasing, is just the fact that you are losing information about the dynamics. So the dynamics itself, of course, it's reversible, but somehow if you lose all the information in the course of the dynamics, you will not be able to go backward. Okay, so it's like you go for a walk, okay, and after the walk that say so twice you have turned on the left and twice you have turned on the right, but you don't remember in which order. of course, there is the probability that you can go back home is very small. Okay, and if it's just 2 times and 2 times, maybe you can do something like this. But if it's 1,000 times on the left and 1,000 times on the right, there is no way that you can go back. Okay, so I think it's really important to understand that there is no paradox here. The Boltzmann equation tells you something on the average, and of course you have lost a lot of information, and it's not possible to go back. But that's not because the dynamics itself is irreversible. This is just because you just lost information. Okay. So now, if you would like, if you would like to be able to go back, you need to keep more information. Okay, and that's something that actually you can do. So instead of looking at this Amplicon measure and just the average of the Amplicon measure, what you can do is to keep much more information by looking at the exponential moments of the Amplicon measure. So this will be a bit more technical, but I hope I can explain. So you see that in the previous slides, or in Lanford's theorem, what you are looking at is just the expectation, of course, more or less the expectation of the empirical measure. Okay, and now you see that you take the empirical measure, you just test it on the function h here, you multiply it by mu epsilon, which is very, very large, and then takes the exponential, and then only you take the expectation. Okay, so what you can see is that if you look at this function, okay, and okay, just assume that you have here, say you can, in principle, differentiate with respect to h. Of course, this has to be given a proper mathematical sense, but essentially, if you differentiate with respect to h and then take this quantity at h equals 0, what you get is exactly the average of the empirical measure. Okay, so this thing here, it encodes much more than the average of the empirical measure. So the empirical measure is just, if you think as this as an analytic function in H, essentially the information that is encoded in the Lanford theorem is just the first coefficient of this analytic expansion. Okay, so this, of course, you have a lot more information in this, and essentially what you should think of, if you think of at this series expansion, is that so the first coefficient here tells you something about the average. Okay, now the second coefficient, what it tells you is, say, what is the correlation between two particles? Now, of course, we saw that essentially the joint probability of these two particles at leading order will be just the product. So it's not really interesting. This information you already have at first order. Okay, so here what you will do is that at second order, you will look at this joint probability, subtract the tensor product because you know already everything about this tensor product. And now just rescale this with a factor mu epsilon. And so somehow what you will do is just to try to have a blow up around this correlation. And so you will go into finer and finer scales, and you will be able to say a lot about these correlations. Okay, so you just remove all the information that you already have at the previous order, and now just try to focus on this correlation, say at 2 particles or 3 particles and so on. Okay, so that's what is called the cumulant. And so all this information is encoded in this series here. Okay, so it's much more powerful too. Okay, and so what you can say with this cumulant generating function, actually you can also say something about its asymptotic behavior when the number of particles is going to infinity. Okay, so you have exactly the counterpart of this Lanford theorem. So Lanford theorem tells you something about the first coefficient, but actually you can look at all coefficients. And so somehow with this description, you will keep a lot of information about all small correlation and so on. And so what you end up with is that actually this in the limit, this cumulant generating function will actually satisfy an equation, which is an Hamilton-Jacobi equation. Of course, I will not write it here. But what is important with this Hamilton-Jacobi equation is that it's reversible in time. Okay, so of course, this is not the same notion of reversibility at the very beginning. At the very beginning, everything was really reversible just by deterministic reversibility. Now it's a notion of stochastic reversibility, but this tells you that somehow with keeping all these cumulants, then you end up with something which is reversible. Okay, so and the second thing is that because you can do exactly the same thing for some stochastic system, and you would end up with the same Hamilton-Jacobi equation. Okay, so it's mean that really your system of deterministic particles, it really behaves up to exponential scales as a stochastic system. So it's not just like the Boltzmann equation where you have this stochasticity, but really if you compare a stochastic system, so where the dynamics itself is stochastic, and your deterministic system with just random initial data, then they behave exactly the same way up to exponential order. Okay, and so when doing all of this, you are able to answer the two other questions that I mentioned. So the first one about fluctuation. So if you look now at the fluctuation, so you look at the Amplicon measure, you subtract the expectation, and now rescale by this square root of mu epsilon. So it's really like the scaling for the central limit theorem. You can prove that this guy will converge to some equation, and this equation now is not a PDE but a stochastic PDE. Okay, so this means that really somehow the uncertainty and the randomness, which was on the initial data, is transferred on the dynamics. So that's more or less the same remark as here, that really you have a very strong coupling between the stochastic system and the deterministic system. Okay, so this you can prove. And if you are close to equilibrium, then you expect that in the stochastic PDE, you have exactly what physicists call this fluctuation dissipation theorem. So fluctuation due to the noise exactly compensate the dissipation of the entropy. So that you can, so here again, you see that somehow the reversibility. And then you also have an answer to question 3, because actually this current generating function tells you something about the large deviation estimate. So what you expect is that the large deviation function is actually the Legendre transform of this function here. So you can somehow estimate that the probability of seeing something which is very different from the Boltzmann dynamics would be exponentially small, and you know this factor here. Of course, you don't know the prefactor here, so this means that the log of this guy is like this. Okay, so and so this is the counterpart of the Langford theorem that we obtained in a kind of huge project with Thierry Bodino, Isabelle Gallagher, and Sergio Simonella, that this cumulant generating function converge in the limit towards the solution of the Hamilton-Jacobi equation. And unfortunately, we still have this restriction on the very short time. Okay, and you can prove that it's analytic, so you get the covariance of the noise, you get the large deviation functional, and so on. Okay, so I just would like to spend the remaining time, or maybe the remaining time minus 2 minutes to have for the question, just to tell you. Not really a conclusion, because at this stage we are still very far from a conclusion for the original problem. So maybe I should go back, but I will not do it, to the original. So the first slide about this big picture. So between the connection between say the microscopic system and the mesoscopic system, so kinetic theory. And I would like to comment a bit about first of all the time. So, okay, this restriction on the time, which is not just like a technical problem, okay, and about this notion of chaos. So these are the two things that maybe are really important to understand, that essentially, first of all, we are stuck. And the other thing is that somehow we say from the physical point of view, all of this is just completely irrelevant, okay? So that's good to know that we are not super strong. We cannot just essentially understand anything from physics. Okay, so the good thing, okay, because there are still good things. The good things is that we are able to completely understand how the randomness is somehow transferred from the initial data to the dynamics. Okay, so that's a very nice thing, and you can really compare once again the deterministic system with the stochastic system. So this is actually rather a good thing. Okay, but so you see that everything here. So if you just try to think about what we proved, okay, so we start from a very specific initial configuration where we assume that all the particles are independent. Okay, and actually, if you look at the gas in this room, there is no way you can just assess that the particles are independent. You don't know. Okay, So you see that now, if you look at the proof itself, what you try to do is to say, okay, this system is not really good because we have collisions, and so each time I have a collision, I destroy a bit the independence, and that's okay, but it's not very important because, say, on a finite time, I can just ensure that, okay, I still have enough independence to write everything. Okay, but you see that from a physical point of view, it's really strange because it means that the more collision you have, the less independence you have. Okay, so somehow collisions are just your enemy. Okay, and now I think it's not at all what physicists have in mind. Say physicists, what they have in mind, and actually it's very clear in Boltzmann's work, is that the reason why you should have this chaos, okay, and now maybe it's more related to the notion of chaos in dynamical system, is that because you have all these collisions, and also because you see that at each time you have a collision, you have this very high sensitivity. So you see that each time you have a collision, maybe you will just change a little bit the parameter, and then you will obtain something which is completely different. Then you have a very strong mixing. Okay, so from a physical point of view, what is expected is that actually the collisions, because say the fact that you have all these collisions, plus the fact that each of this collision is responsible for kind of very strong instability, this should actually generate chaos. So you see that the physical reason why it should be true that you have this Boltzmann equation, and also I think all this Hamilton-Jacobi equation. So everything. So the somehow the mathematical description of the thing, I think it's good. But the reason why you should get this mathematical description is not the right one. Here we assume chaos at the beginning, and then we say that okay, if we just look at a finite time, then this will not be too much destroyed, and then we get this statistical picture. Now, what we expect is that okay, maybe you can start with still with this chaotic thing. So for this first finite time, okay, you will see somehow the effect of the initial data. So okay, you will propagate chaos, but then actually the chaos, of course, in the sense that you have this strong independence, it will be destroyed by the collision, and that's still true. But somehow, because the more collision you will have, the more mixing you will generate, and then you will end up with chaos, but for another reason, which is this generation of chaos by mixing. Okay, and so all these parts, which is actually the probably most important part from the physical point of view, and you see that's a mechanism which is not really described in mathematical literature, not for this system, but for any. To my knowledge, there is nothing like this in the literature, even for quantum system, for wave turbulence, so there are a lot of physical system in statistical physics where you expect this kind of mechanism, that you have very strong instability at the microscopic level, and you would like and you would expect this microscopic instability to generate a very say nice stability at the macroscopic level. And this thing, I think, it's completely open to understand how these things which at microscopic level seems very, very bad, actually they behave in a very nice way at the macroscopic level. And I think that's really a very challenging question for the future in all this field. And I think it's time now to stop. I thank you very much for your attention.
Thank you very much, Laure, for a beautiful talk. I think we have maybe 2 minutes if there are questions in the room over there.
Yes, so maybe there is one.
Can you just repeat the question, please?
The question is about my the two last words of the presentation about the link with renormalization theory. So my understanding is that in renormalization theory, you start with your macroscopic system, and then you build from this microscopic system kind of average system, but just looking step by step. So you start with one particle, then look at the correlation between two, and then the correlation between three, and at each time, at each step, you try to figure out what is the somehow the effects of this more microscopic thing on the macroscopic, so on a more macroscopic level. Okay, and so what I think here is that if you would like to exhibit such a cascade, so the fact that somehow the mixing really come from the microscopic scale and should somehow stabilize all the scales above, then you have really to understand this kind of renormalization. So what is the effective somehow effective effect? Maybe effective effect is a bit too much, but the effective behavior. So just trying to remove, say, transform progressively the deterministic information on the very large cumulants into something which becomes stochastic. So instead of, so here you see that we somehow look at the in the other way. So we start by, say, describing the first marginal with this Lanford theorem, and then say, okay, but then if you know the first marginal, then the second one would be like this or like that. Okay, so somehow we look at the cascade this way. So that is the macroscopic scale and the microscopic scale, and we look at things like this. But I think probably the right way to do that, to understand the physics behind, is just to go the other way. So start from the microscopic, and this, to my knowledge, there is nothing like this in this for this deterministic system, because what you have to do is really to understand at each step how you can transform the instability or the mixing in something which is stochastic, which is the big picture that you have in mind in the end, that say all the instability should be transformed in some stochastic thing. But I think you should do this just step by step. And that's the connection that I have in mind, but nothing like precise statement or things like that.
Okay, very good. Are there any more questions in the room?
No.
Maybe last question, because we're running short.
So maybe just to elaborate a little bit on this. So the time scale would really. Yeah, I was giving. Okay, so to elaborate on this a little bit, the time scale we would really be interested in is the relaxation time, the time it takes for the equation to go to equilibrium. So T star in the theorem compares how to that time? How far are you? I mean, like, you know, if you want to do this renormalization group, how many steps will you have to take? Like,
yeah, actually, I don't understand this problem very well. It's just like, but my impression is that you should not look for a time which would be uniform for all cumulants. Somehow, you see that a very big cumulant, it means that you have a very big clusters of particles which are connected by collisions or maybe overlaps, but say collisions. Okay, and so you have these very big clusters, and if you have a very big cluster, of course, you see that each time you have an edge in this cluster, you see that you have this very strong instability. So something like a Lipschitz constant, which would be of the order of 1/epsilon. Okay, so of course, if you look at the whole thing, then you expect the instability in this very big cluster to be 1/epsilon times the number of guys in the clusters. And so you see that the mixing for this one, the mixing time should be much shorter than the mixing time for say a small cluster. So I would not expect the mixing time to be the same for all, and that's why I think you really need to look at kind of renormalization procedure, just because you cannot do all at the same time. I think that somehow the stochasticity will be important in the big cluster much before it's important. So you would have something like so for you a picture like this. So here you have initial time, here you have the macroscopic scale, and here the microscopic scale. Okay, so the instability is much stronger here. So you should have mixing in a very short time here, and the mixing. So on the macroscopic scale, the time for which you expect, say, to lose the information about the initial data is something probably which is of the order of this Lanford time or something like this. Okay, so you would have something like this would be the region where the initial data is really important, and say beyond this region, then stochasticity or mixing should be more important. this is what I have in mind, but you know, it's just completely science fiction. I think it's really science fiction.
All right, I think we should finish at this point for the live session, and we all thank very much and applaud Laure virtually. And thank you again.